Section 6 in Chapter 4 is called Formalizing Relations and Functions. We've been working with these the entire chapter, so now it's just like, okay, here's what we've been doing so far, and here's where we're kind of heading with them, because they don't go away. We're going to be using these the rest of the year. A relation is just a comparison. I think we may have actually seen these words before already, so just to refresh our memory, a relation is a comparison of two things. Like foot length and height, or eye color and IQ. Those could be relations. They might not be related at all, but they could be relations. The domain is all of the x values in an ordered pair. So like if I have an ordered pair, x comma something, that's the domain. The domain is inputs. The domain is the independent variable. The domain is what we control. Mostly the domain is the x values, though. So the range then is what? The y values. In the ordered pair, it's the second coordinate. It's not inputs, it's outputs. It's not the independent variable, it's the dependent variable. And instead of it being what we control, it's what changes because of change in the domain. So we can represent domain and range using ordered pairs, as I've kind of shown there. I also have shown you that you can represent relations using tables. You can also represent relations using graphs, and that's kind of what we've been doing for this entire chapter so far. If you realize it or not, we've been making tables, we've been making ordered pairs, we've been making graphs. There's another way to represent relations, and it's called mappings. To make a mapping, you first need to identify what the domain and range are. Mappings are my favorite out of the four. So, how do we do mappings? Well, I'll get there, I guess. In a relation, you have a set of ordered pairs. So here is a relation right here. It's just a comparison of a couple of things. 2 with 5. 5 with -2. -1 with -2. What's the domain? All the x values. So I'd write D for domain equals, this is a set, so I'm going to use the squiggly brackets again. And all the x values are just 2, 5, and -1. So what will I write for range then? R equals, squiggly bracket, what? 5, -2, and then we have -2 again, and we don't write the repeats. Have we talked about that? Okay. We don't write the repeats there. So you're also asked to make a table, a mapping, and a graph using those ordered pairs right there. So to make a table, all you do is what we've been doing. X and Y at the top of the table, and then you write all your ordered pairs. 2, 5, 5, -2, -1, -2. That's all you got to do. I'm going to skip the mapping for now. Let's go on to the graph. To graph 2, 5, we've been doing that as well. Go to the right 2 and then up 5. Put a dot. Go to the right 5. So there it is. And then -2 is right there. And then -1, -2. And I'm going to label these ordered pairs also. -1, -2 is right there. And that's 5, -2. and then that's 2, 5. Yeah, it kind of does make a triangle. To make a mapping, here's what you do. You have to identify the domain and range, it said earlier. So the domain we've already identified, the range we've already identified. I'm going to put a capital D and a capital R like that, and then I'm going to draw ovals. Inside here, this is kind of like a Venn diagram. Inside this oval is going all the domain values. So 2, 5, -1. They don't have to be in numerical order. You can just write them in there the way that you see them. For the range, I'm not going to write any repeats. 5, -2. And some of you have probably seen this before. What do? Draw arrows. Yep. So I'm going to change colors because I can. You guys probably can't. But what you do is you say, okay, 2 in the domain. Up here, 2 was with 5. So you're going to say 2, draw an arrow over. And the way you would read that is 2 maps to 5. That's why it's called a mapping. Then you say 5 maps to what? -2, because up here it's 5, -2 as an ordered pair. So I draw an arrow over to -2. It is supposed to be an arrow. It's not just a little line. And finally, -1 maps to what? -2. So from here, I draw an arrow to -2 as well. So on the mapping, you can have arrows going to the same number in the range. On the mapping, if I had a repeated domain value, then I would see an arrow coming out of the same number. Okay? You can have arrows going into the same number. You can have arrows coming out of the same number. That's how you do a domain. One thing I want to add is when we write down repeats and when we don't. When we're writing ordered pairs, we do write down all of the ordered pairs. When we're making a table, basically you're just turning those ordered pairs into table format. So I will write down the repeats there. When I'm doing domain and range, I do not write down the repeats. So I had no repeats in the domain. I did have a repeat here with that -2. I did not write it down. When I'm doing the mapping, I also do not write down repeats. The reason we don't write down repeats in the mapping is because we want to see arrows coming out of the same number or going to the same number. And if you just write down all the numbers, all you're ever going to do is draw arrows across. And you'll never see those arrows going to the same number. So no repeats in mapping. And in graphs, obviously, you're just graphing ordered pairs, so you're just plotting points there. So here's a new relation for you. We have 4 ordered pairs. Determine the domain and range. So for part A, what are we going to write? D equals. Now what? 4, 3, -4, and 0. Didn't have any repeats to worry about. Now what? R equals -3, 2, 1. What about -3? That's a repeat, so I don't have to write it down. Okay, that's it. You don't have to put them in numerical order. You don't have to do anything. Just write them down as domain and range. Domain is the x values, range is the y values. How about the table? What do? X and y. Got to label your columns. And then just write down your order pairs. 4, -3, 3, 2, -4, 1, 0, -3. So I guess that line should come down a little bit. There you go. For the mapping, what do? Draw a couple ovals. Now what? Label the top, the domain, and the range. You have to have those labels on there. Now what? Okay, so what goes in this oval? 4, 3, -4, and 0. Good. And what goes in the other oval? Negative 3, 2, 1. Now what? Draw the arrows. So 4 maps to negative 3. 3 maps to 2. Negative 4 maps to 1. And then 0 maps to negative 3. So how am I going to do that? Do I need to draw a little squiggly arrow, and then loop it all around and then sneak it in right here? Am I going to do that? Just draw a straight line. It's okay to cross those arrows, okay? Don't try to be cute and loop it all over the place and make a little maze out of it. Don't need to do that. I'll get lost and then I'll get annoyed and then I won't look at it anymore. Okay? It's okay to cross. Now the graph. How do I graph 4, negative 3? Right 4 and then down 3, and I'm going to label that 4, negative 3. Now what? Over 3 from here, so this way. Go to the origin. Go right 3. And then up 2. That's where 3, 2 is. So label that 3, 2. Now what? Go back to the origin. Left 4. 1, 2, 3, 4. Up 1 is correct. And label that negative 4, 1. And one more. Origin. Down 3. And then what? Oh, that's it. And label that one. 0, negative 3. So that's how you do those problems. You're going to need to pay attention to the directions in the homework because they're going to ask you for some combination of these, or maybe all of them, maybe one of them. So just make sure you know which one it is that you're supposed to be doing. In order for a relation to be a function, have we talked about this before? Okay, well, how does a relation become a function? If what? No repeated x values. There are other ways. The vertical line test. It needs to pass the vertical line test. How to tell if a relation is a function with mappings. If I don't have any repeated x values, then it's a function. But in a mapping, I don't see the repeats, I see arrows. So in a mapping, if it's a function, then no arrow, no more than one arrow leaves any number. If I see more than one arrow coming out of a number in the domain, then it is not a function. So we have 8 problems here. Each one of these problems is different. We need to decide if each one of these is a function or not. I think you've seen a few of these before. No big deal. We can do them again. Is this first one here a function? Yes, because there are no repeated x values. None of those are the same. How about this table? Is this a function? No. Why not? Yeah, in the x column we have repeated ones here, so this one is no. How about this mapping? Is that a function? Yes, because if you look at the domain, there's only one arrow coming out of each one of these numbers, so this one is yes. And how about this last one? Is this one a function? Why is this one a function? It passes the vertical line test, so that's a yes. How about the second set of ordered pairs? No, because we're looking at the x and we see a 4 repeated in the x value, so this one's no. Notice that I don't care at all about the y values to tell if this is a function or not. How about in this table? This is a function. Even though I have repeats here, that's okay. The answer is yes here. How about in this mapping? Is this a function? No, it's not. Why? Yeah, notice in this 1 right here, I have 2 arrows leaving that 1. That means that the 1 was repeated, so that we had to draw an arrow coming out of it once and then another arrow coming out of it again. That is not a function. And how about this last graph? No, definitely not. It does not pass the vertical line test. The other thing that we have to talk about in this section is called function notation. You've been seeing equations that look like y equals 3x minus 8. You've seen this before, right? This is function notation for the exact same equation. You still see the 3x minus 8 sitting here. What's different? On the one we have y, and on the other we have this f with parentheses and x. Okay? This right here is called function notation. It's just a name. That's all it is. It's like if your name was John, then people would call you John, right? And then when they were talking about you, you would say, or when people were talking about you, they would say, John did this, right? They're just using your name. So we have f of x. That's the name of this function. That's all it is. This is not f times x. We're not going to distribute the f in. This isn't like something we can get rid of. We're not going to divide the entire equation by f. This just stays what it is, okay? It's just another way of writing down a function. And the reason that we use function notation is sitting here. First of all, you know which variable is the independent variable immediately. In this one, we're assuming it's x. But in this one, it is definitely x. Because what this says is, here's x. I can change it and make it whatever I want. This completely depends on what happens to x. That's why it says this is a function of x. As x changes, what happens here? Okay? So now I know which variable is the independent variable automatically. So that's why function notation is really nice. The other is you can easily substitute and keep track of what you're doing. So we've been making tables, like XY tables, and each time we have to write down each ordered pair. Well, with function notation, it's sort of like a record-keeping thing. We can use the function notation, and then when we look at our answers, we know exactly what it was that we found. So, for example, if f of x equals negative 4x plus 7, you can think of that like y equals negative 4x plus 7. And now they're asking me to find out what y is when x is 2. That's what that says right there. So instead of me saying, remember mathematicians are very lazy, if I had y equals negative 4x plus 7, then in order for me to ask you what the answer to that problem is, I would have to say, what is y when x is 2? What is y when x is 2? That's 7 words. Instead, using function notation, all I have to do is say, what is f of 2? It's easier. It's faster to say that. And it's better because now all I have to do is substitute in 2 for x. See how it was f of x and now it's f of 2? All they did was turn x into 2, which means over here I turn x into 2. And then I can simplify that down. So I'm going to write negative 4 parentheses 2 plus 7. I substituted in the 2 for x. So now I get f of 2 equals negative 4 times 2 is negative 8. And negative 8 plus 7 is negative 1. That's my answer. Remember that f of x is just a name. We're not going to solve for f. We're not doing anything to it except for substituting in that 2. And then that tells me what to do to the actual equation. So next, f of negative 3. What am I going to do? Substitute in the negative 3. So I'm going to write f of negative 3 equals what? Good. And then I write f of negative 3 equals negative 4 times negative 3 is positive 12 plus 7 is 19. So now notice we're using the exact same equation, and we've now plugged in 2 different numbers. We have 2 different answers here. But now if I come back later on, because it's commercial break and now I can continue, I know exactly what I did to get this answer. I know exactly what I did to get this answer. That's the nice thing about function notation. How about that? What does that say? Doesn't say hard at all. Actually, this is easier than the other two. Instead of x, it's a. So if I were to read this, I would say f of a, okay? This is f of x. This is f of 2. This is f of negative 3. So f of a, all that says is substitute a in everywhere you see x in the original function. So I'm going to write what? Negative 4. What is negative 4 times a? It's negative 4a. So I'm just going to write f of a equals negative 4a. And I can't do anything with that 7, so plus 7. And that's it. I'm done. It's actually a little bit easier, I think. All you're doing is trading variables, pretty much. Okay, we have a different function here. Notice that it's called h of x. That's no big deal. You can use f of x, you can use g of x, you can use h of x, you can use w of t. It makes no difference. It's just the name. So now this is a different function. It's like a different person. 3x plus 4. Find each of these. H of 0. What am I going to do? Substitute 0 in for x. So I write h of 0 equals 0. Okay, what is 3 times 0? So what do I get for h of 0? 4. That's it. H of 0 equals 4. How about h of 5? What am I going to write? 3 parentheses 5 plus 4. So h of 5 is 15 plus 4, which is 19. Let's do this one here, h of negative 3 first, and then we'll tackle the third one. So what am I going to write? Okay, so h of negative 3 equals what? Negative 5. 3 times negative 3 is negative 9. Negative 9 plus 4 is negative 5. This one, a little bit more complicated. It's asking me to find h of 2, and then whatever h of 2 is, add 4 to it. That's all it's saying, okay? So h of 2 first, and then plus 4. So I'm going to write equals h of 2. So I take 2 and I plug it into here. 3x plus 4. Let me change that. I don't want 3x, I want 3 times 2. 3 times 2 plus 4. That's the h of 2 part. And then it says add 4 to that. So plus 4. You guys okay with that? Okay. Well, 3 times 2 is 6. 6 plus 4 is 10. 10 plus 4 is 14. So there's your answer. All right, a couple of examples of how we use function notation. If you're asked to find the range of a function, you're given the domain, find the range. That's what these problems are asking you to do. Here is the domain. 1, 2, 3, 4. We want to find the range. What that means is take each one of these numbers and substitute them in, just like we were just doing. So you're going to have to solve this problem how many times? 4 times, okay? Now that's why the function notation is so nice, because I'm going to be able to write f of 1 equals, f of 2 equals, f of 3 equals, f of 4 equals. The answers that I get are going to give me the range, so then I'll be able to write the answer. So we have f of 1 equals negative 1.5 times 1 plus 4, which is negative 1.5 times 1 is negative 1.5. Negative 1.5 plus 4 is 2.5. How do I get that? Using my head. I added. Yes, you can. 4 minus 1.5. Think of money. You have $4, you spend $1.50. You're left with $2.50. I take 2 and I plug it in. Negative 1.5 times 2 plus 4. What's negative 1.5 times 2? 3. It's negative 3 plus 4, which is 1. F of 3. So now I write negative 1.5 times 3 plus 4. What is negative 1.5 times 3? Negative 4.5. Good. If you can't think of that one, think of like 15 times 3. 15 times 3 is 45. So 1.5 times 3 is 4.5. Anyway, this is negative 4.5 plus 4, which gives me negative 0.5. And the last one, what am I going to write? Negative 1.5 times 4 plus 4. What's negative 1.5 times 4? Negative 6. Negative 6 plus 4 is? Negative 6 plus 4 is negative 2. Okay, so we have these answers here. F of 1 is 2.5. F of 2 is 1. F of 3 is negative 0.5. F of 4 is negative 2. It says, what is the range? Well, then you're going to say R equals squiggly bracket, and then just write your answers down. 2.5, negative 0.5, 1, negative 2. And I wrote that in a different order than what I found them in, but that's fine. It doesn't matter. So what should I do on the next one? The same thing. What am I going to write? G of 1 equals show the work times 1 minus 12. What do you get? That's 4 minus 12, which is negative 8. Then I'm going to write G of 3 equals what? Minus 12, and what do we get? 0. Then we're going to write what? G of 5 equals 4 times 5 minus 12, and we get positive 8. And then we're going to have G of 7 equals minus 12 equals 4 times 7 is 28, so 28 minus 12 is 16. That's the nice thing about function notation. It's all nice and labeled, so you know exactly which one goes with which number. And then we want to write down what the range is here, so I'm going to write what? Before that, R equals what? There you go.